And this time we'll just concentrate ourselves on the cycles of very important element for our life and for our environment. And those we'll look at the cycles of carbon, nitrogen, and phosphorus. Those are the major component of the fertilizers and the major component of the environment, trees, food. So they are producing glucose and some other organic lipids as well. So we finished almost half of chapter 2. This time we should finish chapter 2 this week, and if the time permits and finish on time, then we'll go for chapter 8. So I'm following the other professors in geology. They are teaching the same class, so I told them I will be in the same wavelength and the same speed and the same space. So that's what we are doing. So the first thing here is nitrogen, phosphorus. As I said, those are the major elements contributing to the well-being and the food of our producers, which are the trees. So producers are really mostly are trees, and those are very essential for a whole human and for the whole type of lives, whether it comes from bacteria all the way to animal kingdom. So from bacteria kingdom to the tree kingdom to animal kingdom, marine life kingdom, all those are depending on those nitrogen and phosphorus. It's very, very important elements in our life. And you can see why they are very important. Besides carbon, they are producing glucose and some other glucose-related compound, correct? Like nucleic acids, lipids, sugars. So those are very essential for keeping the metabolism and keeping us walking, keeping the trees are alive. So those are the elements. Phosphorus and nitrogen is very, very important. So, and we will go through all this and see how they start their cycle. But before that, we have to look into the energy here. Now, because I'm a chemist, I put for you, that's in iCollege already in the folder. You can see it there. The energy. Energy is ability to do work, correct? And the energy is really very important. That's what our bodies are, and all the living creatures are using this energy to survive in our environment and in this planet. So energy, ability to do work, and the energy can be divided into kinetic energy and potential energy. The kinetic energy is any time you have a moving object that will have, you don't have to worry, but I put this one here for you. But at least you will know when I say kinetic energy, you'll ask yourself what's really kinetic energy is all about. Well, it turns out the formula for the formula, although it's the textbook is missing this because it's not a chemistry class or physics class, but I think it's better to get the idea what's really the energy is. Energy is sometimes is called heat, which is recognized by transferring the temperature or the heat from one object to another object and see the difference in temperature. So kinetic energy here is half of the mass of any object multiplied by its velocity square or speed square. So mass, and this one here, V is speed, and is squared. This is kinetic energy. Anything moving, it will have kinetic energy. So, and this, the formula of kinetic energy is half the mass, whether it's a 18-wheeler or me or anybody is moving, anything is moving, that's moving object will have this kinetic energy because you have the speed, the velocity, that object is moving, and you have half of its mass. The velocity square, this is square here. Okay, this is square here. Okay, so that's the kinetic energy. So the kinetic is energy is made of kinetic and potential energy. Well, it turns out the potential energy formula is not half of the mass because there is no motion at all. So there is the mass. So this is the mass here, and this velocity or speed. This is the mass, correct? That's the mass here. Multiplied by the gravity, earth gravity here, multiplied by the height that object is found in. For example, I have a rock here. That's a mountain here. There is a rock. That's a mountain here. This rock is at rest, not moving at all. It possesses only potential energy. Only. Because it's at rest. Since I'm starting moving it, this rock here is moving now downhill. So this potential energy is moved or converted into kinetic energy. So it started with mass multiplied by earth gravity multiplied by the height. The height is from the top, the summit of the mountain here, to the bottom of the rock. That's the height. And the earth gravity, you can look it up, and the mass of the rock itself. So at rest, no motion, no nothing, this rock will possess potential energy only. Now I knocked down this rock downhill. Now the potential energy is converted into what? Into kinetic energy. Hold on. Let me maybe, can I take this one here? I will have this one here and this. Bless you. So here it is. Let's put this one here in perspective and look at the whole thing together here. Let me take this one out. So now we have, let me just repeat this one here. So we'll have this picture. So there is a rock here. Okay. And there is a mountain here. This is mountain here. And then start this is from the bottom here of the mountain, from the bottom of the to the top. That's the height. So this rock possesses only potential energy, correct? This is the height. So the potential energy here, E, potential, E pot. Potential energy is mass multiplied by the earth gravity multiplied by the height. So this is earth gravity here. This is the height. And we said kinetic energy is due to motion, and potential energy just stored in the object itself. Now I'm not talking, if I'm not talking standing here, I do have potential energy because my height to the savanna sea level. So from here to the height from my height here is here at this to the sea level at savanna. That's my height. And the earth gravity and my mass, my weight. So therefore I can determine my potential energy at a localized point, correct? So then I'm moving this this rock. I'm moving this rock here. I'm moving this rock here. So this rock is being moved. So here it is, here it is. Now somebody is standing here without knowing. If somebody's standing here without moving, and this rock will come and hit the foot of that person. I'm not an artist. I'm trying to. I'm not an artist. So now we have this potential energy at rest, no motion, converted into what? Now this energy here is now kinetic energy. Because now we have in motion, this rock is going downhill. We have kinetic energy, which is half of the mass multiplied by velocity or speed square of the speed of this rock going down. Now, when it hits the foot of a person there, the person will feel the pain, correct? It's a rock, it's heavy, and it has this amount of energy here. This energy, the kinetic energy, so we have, this is potential energy here, correct? This is kinetic energy. Now here, the hit here, the person feels the impact, correct? The person feels the impact. This impact now is called work. So now we know that this energy came from potential energy to kinetic energy to exercising work. And that's I feel that person feels the pain in the foot. I don't see the energies. Can I see the kinetic energy? No. Can I see the potential energy? No. But I feel the impact of this kinetic energy being converted into work, and this work of motion is affecting the foot of that person. Feel the pain. Feeling the pain is work. So it's work is being done on this foot of that person, correct? So that's the reason. So energy means it's not really destroyed, correct, or created from nothing. Energy always recycling itself. Potential, kinetic work back to, because then the rock will what? The person will take the rock and leave it on the earth. Maybe this level here, there is a valley down, so there is a height. So the work will transfer into what? Potential energy again. And then you can from this area dump it to the valleys, and then they can always recycle itself. Energy is always recycling itself. Everybody's following me here? So that's not in the book. I wish that it should be there. At least you don't have, that will be not in the quiz, but at least you get the feeling that there is no energy will be destroyed or created from nothing. Always, if it's created, then it will be in a pool, in a circle, in loop, back and forth, correct? And the total energy is here, the total one, which is, the total energy is the potential energy plus kinetic energy. So the total here, this is a low here. The total energy is potential plus kinetic energies here. Any questions so far? Somebody has it? It will be in the recorded inside the lecture recording. So can I take it out? Take it out? You can take snapshot of it anytime. You can take snapshot of it. So I'm taking this one out, going back to the PowerPoint. I said that's it's better to have something about the energy, correct? So kinetic, as I said, it comes in a very way: solar energy, wind energy, electricity, heat, light, sunlight. All those are different types. Chemical energy from the batteries. So all those types of energy, but at the end, it comes out to potential plus kinetic. Potential plus kinetic. Correct? So, and here just an example. I'm not going through this, but here is, you can see the waterfall is here, and you see, and if we have a rock on the top of this waterfall, those rocks will possess potential energy because they are not moving anywhere, while the water itself in the waterfall is moving, correct? The rocks on the top, they possess potential energy, while the water going down the waterfall, they will have kinetic energy, correct? So that's the kinetic energy. Potential energy, we said any mass multiplied by Earth's gravity multiplied by the height. The height is the level from that object found into the lowest level far away from that object, and it's really potential energy. Anything can possess a potential energy. As long as it's not moving, you will have, and there's a specific height there, then you will have a potential energy, correct? And this is stored energy is used for it's like standby energy, and used whenever somebody need it, then that object will be using it, the body is using it. And there are some examples here: rock at the top of dam or rock of the waterfall. They possess potential energy, correct? Energy, chemical energy stored in food you eat, gasoline that you put in your car, all those are potential energy. As an example of the total energies are kinetic plus potential means gives you the total energy. The total energy is made of the addition of potential energy plus the kinetic energy. They convert themselves, and at the end they go to work, and work can go back to potential energy, kinetic energy, work, and it's like a loop, correct? That's like a loop. Heat always is energy, and don't come to the idea. We say all the time we have a negative. I don't know where my picture is. We have, as I said, we said every time somebody has negative energy, correct? You heard about the word negative energy? Mm-hmm. But do we have a negative energy really? No. Energy is always positive. There is no negative energy. There is, by all means, in chemistry and physics and engineering, there is no negative energy. But there is a possibility to find negative energy in this universe. Somebody will tell me where? Somebody will tell me where we might find negative energy. Somebody will tell me? No. Did you hear about the black holes in the universe? Black holes is like this vacuum machine sucking the dirt. And the black holes is like a vacuum machine that's sucking anything in there. And black holes are vacuum machines. They suck everything in their vicinity. Stars, meteoroids, planets, anything in their vicinity, They look like a black hole in the universe, but it's like sucking. They have sucking power into them. Now, scientists, they think that it might be inside this hole. We don't know. All the physics we know, all the chemical reaction we know, all the nuclear reaction we know will be upside down. And there is a possibility that even the energy will be negative there, because we don't know what's going inside those sucking power vacuum machine called black holes. Okay, guys? So that's what it's saying. So now, that's the heat here, and we can study the heat and the energies through first law of thermodynamics and the second law of thermodynamics. Now, I put this one for you. You don't have to memorize the formula, but the formula will give you some feeling. They will not come in the midterm. They will not come in the final. Whatever is in your ebook, the book you have, the ebook, that will come. But those are things I give you just to give you the idea what's going on. The first law of thermodynamics will really about conserving these energies. And I put for you the let me show you here in a minute. What's the first law and the second law? The first law of thermodynamics is given to you is, I give you the kinetic energy is there inside iCollege. The first law of thermodynamics is the internal energy. Internal energy here is equal the heat minus work. Heat minus work. That's what it says. It's about, first is expressing the heat and the work together relationship in performing or producing internal energy. So the internal energy U change equal to heat minus work. And I did not explore this further. We can explore it further. We say the heat we know, that's this expressed in temperature, correct? And the heat is mass multiplied by specific heat multiplied by difference in temperature. While the work here, whoops, sorry. Let me back off here a little bit. I take this one here or copy it. I hope it will copy. And then I put this one here. So that's not in iCollege. I put this one not, but at least you will know when somebody will ask you, what is really work? Well, it turns out to be, that's not chemistry, that's not physics. That's an extra information. That will come in the quiz, I promise you, and not come in any midterm or any final exam. But I like to have my students have a little bit of feeling towards those formulas. When I say, what is first law of thermodynamics? Well, it turns out the work here, the work here, this is work. What I said before, when you have potential energy goes to kinetic energy, it hits the foot of that person feels the pain. The pain is the impact of kinetic energy, which is work. So the work is negative pressure multiplied by delta volume. This is pressure here. And this is delta means change. And this is volume, change in the volume. That's the formula of work. You don't have to write it after me, but at least you get the feeling when I say, well, what is work? So that's the formula of work. The heat, on the other hand, Q is the heat and is defined as mass multiplied by the specific heat multiplied by delta T. This is specific heat, which is the ability to retain heat. How much is this object or this body is retaining heat? And this is change. And T is temperature. Again, I'm putting here in my recording. This one will not come in the quiz or midterm or final exam, but at least I give you the idea when you hear about first law of thermodynamics. Well, what is first law of thermodynamics? The sentence, but you can't have the feeling of, so the internal energy here, this is called internal. Internal energy here is nothing less than just the heat generated, which has this formula here, minus work, this formula here. Okay, guys, you don't have to worry about anything else. This is just an extra information about the first law of thermodynamics. The second law of thermodynamics would deal with entropy. Can I take this one out? Everybody has it? Again, I'm repeating myself again and again. This one not part of the quizzes, midterm, or final exam. This extra information not found in the book. I said it's better to have the students having the feeling when I talk about heat, energy, all this stuff. You can get formulas for those. So, the second, if this one here will tell us the entropy, the second law of thermodynamics is about entropy. Entropy is the arranging of things, the order of the whole universe, of the whole environment. So it looks like the entropy here will increase. So the first law of thermodynamics will predict that there is an end of what? Of the whole universe. The whole universe one time will collapse. Are you following me here? Nothing will be on this whole universe. Everything will be collapsing. And that's predicted by the second law. The second law of thermodynamics tells you that the disorder in this universe is increasing, like we are here. The disorder increase to the point that the whole thing will explode. The whole universe came from condensed one mass and exploded in too many galaxies and too many stuff, correct? Now we are back from this disorder, will go even bigger, and the whole thing will just explode. And that's what we call day of judgment, whatever you call it. That's the end of the universe. And that's predicted by the second law of thermodynamics. That's the universe. The entropy is here. Let me just write it for you guys. Entropy always predicting. That's the first one. You can take it out. So the entropy here give us what? Degree of disorder of our environment and the whole universe and the whole universe. Okay, guys? So that's call it the entropy called S. So any change, this entropy change, we call delta S. Delta S is change in entropy. The triangle means change. So the change of entropy will increase to the point that the whole universe will collapse. That's predicted by this disorder of the degree of the universe itself. So can I take this one out? Everybody has it? Again, those are extra information. I think it's mentioned there, but it's not explained in some detail. So let me take this one here. And here it is. This is second law of thermodynamic equation. That's the entropy change, the disorder change in the system plus its surrounding, okay, is increasing greater than zero. It's increasing per time. And it will come that the whole thing is, the universe is really the whole thing here. So the universe is, let me just here, this delta S universe. Let me just take it here. Oops, where is it here? So here it is. I'm pasting this one here. What's really is here, if you look at this, the universe here, it's not allowing me to write on it, but we write here. So the change or disorder degree in the universe is I don't know why it's not writing. So here it is. For some reason it's not writing. I don't know why. Let's see here. Right. Medium. Okay, let me see if it's writing here. I don't know what's happened to this. So it's not writing. I don't know why it's not writing. Let me escape. Hit escape and that might work. I don't know, it's disabled or. Okay, so for some reason the pen is not moving anywhere, so I don't know why. Although, let me see if it's, I don't know what's happening here. Let me just hold on. Let me take this one here out. I don't know what's happened to the software. So even it does not want even with the mouse. But anyway, so the universe itself here, if you look at the universe here, the universe is made of delta S system plus delta S surrounding. So the universe is the top and the bottom, they are equal. So the top and bottom, they are equal. So let me try maybe this one here. Okay, guys, I don't know what's happened to the pen. Is not moving anywhere. So, and this one here is not. How about the other one, the thicker one? Maybe it's working. Well, both pens is not working. I don't know what's happening. Maybe. So let's see here. Guys, I have no idea what's going on with the software. The software is not reacting. Now it looks like it's, yes. So delta S universe is equal delta S system plus delta S surrounding. And the second law of thermodynamics predicting the collapse of the whole universe. So that's really is. So going back to the back to the PowerPoint. That's what entropy. Entropy tends to increase to all natural systems, and it will end up collapsing the whole environment, the whole universe. So, energy of life, as you can see, we have the energy of life, as you say, the sun is the ultimate energy source for the whole, not the whole universe, or our Milky Way. galaxy. So the sun belongs to Milky Way galaxy. But we have thousands and thousands, and maybe billions of galaxies. I don't know how many galaxies out there, but they have their own source of energy like us. They have suns, which might be bigger than our normal sun, correct? Because the system, our whole universe has to be what? Close to each other, correct? Why? Because it came from one pot, from one mass, and explode to masses, correct? Making planets, making stars, making meteoroids, whatever, making black holes. All this from one spot, one big mass. Now, the sun is for our galaxy, Milky Way galaxy, is the major source of energy. We like it or not, if the sun will move towards us, the Earth, a little bit, couple of degrees, will be what? Will be barbecued. If the sun goes away, couple degrees out, will be frozen to death. So it's a very important energy source for us, and we're really depending on our major source of energy from the sun. Now, the energy is captured by the green plants. All those green plants or the tree will have for them now a new name called producers. They are producing. They are producing our fruits, our veggies, our whatever you call it. Those are called primary producers. So now when we talk about trees, we talk about primary ones. Because all our veggies, all our fruits, all our stuff is coming from what? From those trees. And you will see some of the animals are eating those type of fruits or type of veggies or type of trees to sustain life, correct? And this primary producers are as you will see, through the chemosynthesis and photosynthesis, they are making what? They are making glucose. They are making energy. That glucose is a source of energy, we know. So it can be used to sustain life in this environment, in this universe. So they are producing, the producer producing a lot of, as I said, food for us and for other creatures, animals, and even insects, and some they are using the air, the carbon from the soil, and the air which has oxygen and carbon dioxide. Now, we have two syntheses we have to look into that: chemosynthesis, and we have photosynthesis. What's the difference between chemosynthesis and it is chemosynthesis and photosynthesis? Well, in both, the common feature of those, they are producing what? Glucose, correct? They are photosynthesis are at the end of the purpose of synthesis of photosynthesis is to produce food for the plants themselves. In order to produce veggies or fruits, whatever on them, they need energy, they need food, and therefore they are producing glucose. Now, this glucose can come from inorganic compound, such as hydrogen sulfide, and the hydrogen sulfide comes from volcanoes, or from volcanoes in the sea level, or just from the volcanoes on the earth. So some organism here, they take this hydrogen sulfide, they take CO2 with it, and carbon dioxide and H2O, just tabor, from the ocean, and they get the chemical reaction, and some bacteria, they help them to break in this H2S, the sulfur oxidizing bacteria. At the end, they produce what? They produce glucose. So at the end of the whole chemosynthesis is producing for the those allergies or whatever creatures inside the sea. That's mostly in the sea, in the ocean. So they are producing those type of organisms, producing glucose, and they are then producing energy, which is used for their food, and they're producing for their energy. So it is that's not in the. Oops, sorry. That's chemosynthesis, production of glucose, which is the source of food of those organisms, and through the inorganic hydrogen sulfide. Now we have photosynthesis, the same thing. You are producing glucose at the end, sugar, carbohydrate, glucose, and this is produced in the sense you have oxygen from the air, carbon dioxide from the air. They come with the help of light. Light is acting like a catalyst. They will come and combine themselves to make sugar, which is glucose. Okay, so you have three components there. You have oxygen, carbon dioxide from the air, and H2O from the soil with the catalyst light, and then you get at the end glucose, which is sugar. So both chemosynthesis and photosynthesis is the idea of producing glucose, which is the major source of energy and food, correct? And at the same time, for the main producers, which is the main producers are the trees, whether you get it from trees inside the ocean, which is they are using chemosynthesis, H2S, or on the soil, on land, they are producing sugar, which can be there. By the processes here, the plants are taking CO2, kicking out what? Oxygen. So you have CO2 and H2O, H2O from soil, CO2 from the air, the sun, and then they are kicking out oxygen, which is we really need for us. So that's the photosynthesis, correct? So photosynthesis on soil and chemosynthesis producing glucose. Both syntheses are producing glucose, but one on the soil, one is inorganic hydrogen sulfide, mostly on in the ocean. Okay, guys. So okay, so from now on, we said no more trees. We call them primary producers. They are producing a lot of food for animal kingdom, for insect kingdom. So they are producing primary producer. So, and they get their own food and their own energy here through the synthesis of glucose, through the H2O and CO2, carbon dioxide, and tabor from the soil, correct? So we talked about photosynthesis, and this is the radiation from the sun. And I want you to look into this one here. This is the range we can see. That's the visible range. So we can see each other through this range here. You can see how small this range is, from 400 nanometer to 700 nanometer. Just we have about 300 nanometer, we can see each other. Now, some animals, like owls, for example, they can see underneath infrared. We cannot see infrared. We have to have, the military goggles in the dark. We can't see in the dark, but we can use some specific technologies like military goggles. We can see in the night. So infrared goes to microwave to radio wave. You go here, the energy from the radiation from the sun, that's all is in the sun, will go what? If you go this way here, the wavelength will go, sun energy will be less, will get down. But the wavelength will be high. So this is the energy here. The wavelength here will be high of this radiation wavelength. Here lower, here higher. So going left, you get what? You get higher wavelength of this radiation and lower energies. Going to this way here, to gamma ray, ultraviolet from the sun. Ultraviolet comes after that, X-ray, gamma ray. The energies are very high. Energy will be very high. The wavelength, on the other hand, is less. Wavelength is small of this radiation from the sun. This is the sun radiation wavelength here. Okay, guys, so you can see that which one will penetrate our bodies? The left type of radiation or the right side of the radiation? Somebody will tell me, please. Which one will penetrate our bodies? Left, correct? Thank you. Left. Why left? Because they are high energetic. So X-ray can go through and you can make an X-ray film, correct? Because the X-ray radiation will go through your body with high energy. Gamma ray will go through your body, but will barbecue your body. Are you following me here? So if I have a machine that can produce gamma ray, it will go through the concrete, correct? Go through concrete or whatever, it will go through it because it's so highly energetic. But with this, it generates a lot of heat. So that's killing. You cannot get, and they cure sometimes part of cancers using very minute amount of gamma ray. But you have to be careful. If you add more doses of gamma ray, that patient will be in front of you barbecue. You can see it's really barbecue. Nothing will come out of it. It's just charcoal. So the X-ray going from ultraviolet, X-ray, gamma ray, those are high energetic and they can cause what? Cancer. The exposure of those energies, especially X-ray and the gamma ray, can cause mutation of the cells. Can cause what? Mutation of cells and can cause tumors and then cancers at the end. The other side, they are less energetic. They are harmful, but still can cause damage, but still harmful. Radio waves are really harmful compared with the X-ray and the gamma ray. The ultraviolet is still harmful, correct? Can cause a lot of damage for our eyes and for our skin, correct? So can do a lot of damage, but not compared with X-ray and gamma ray. So, but we see only this. We cannot see in the dark. That's dark, correct? And this is very light. That's very bright. So the area dark, bright, and we cannot see in both. In the dark area, you have to have special technologies, and the ultraviolet, you have special technologies to see them. But gamma ray, we can't really see it. It's so energetic, but we can't see the effect of it. Just put any animal there, dead animal, with all the flesh and everything dead. That dead animal will be barbecued. You see it like charcoal, correct? If you expose that animal to dead animal to gamma rays. So, okay, guys, that's it. This is just the source of energy coming from the sun. See here. Okay, now this is I don't know why it's not showing, but it should be really doing this. The author should show the arrows very well. So the arrows are not good. So if I am releasing energy, this process called combustion or respiration, combustion. So this way here, is called respiration or combustion, reacting with pure oxygen. So you are breaking down the glucose, the trees are breaking down the glucose, feeding it this glucose and breaking it down and releasing the combustion. So breaking down and getting what out of it? The whole effect of respiration or combustion is to get this endothermic reaction. You get to release energy. The whole idea of the combustion or respiration reaction in the trees to release to get this energy. Okay. The opposite way, if you take this energy from the sun, and remember if you take the energy from the sun, add to it CO2, add to it H2O, this way here called what? What called? Photo? Correct. So those are reversible processes. This way, respiration or combustion. The other way is photosynthesis. Photosynthesis is producing of glucose and releasing what? They are releasing this oxygen to us to inhale it. Here, the combustion processes, you are releasing energy which can be used by the trees. Okay, guys? So that's two arrows. This is not one arrow, two arrows. It goes back and forth. Respiration or combustion is from left to right, but from right to left is photosynthesis. You are producing glucose. So then we have here, look at this. This is just to show you the energy exchange, as we said. This is a process in a loop. Remember I told you reversible reaction? From left to right, you are producing energy, correct? That's we call it respiration or combustion. From right to left, photosynthesis, you are producing glucose and releasing oxygen to the environment. So that's the ecosystem here. And the trees are called now, we call them what? Consumer or producer? Producer, correct, not a consumer. Here, this animal rabbit here is just an example for what to being produced. Example for the not a producer but a consumer. So it's feeding itself on the trees, correct? Now when it dies, it will be what? Decomposer, and it's the bacteria inside the soil will break down those dead bodies of those animals back into the cycle, correct? Inside the soil, those elements will be broken in pieces and then back to the soil, and then from the air, and then releasing, as you can see, you're releasing out of this, when you are releasing then CO2, H2O through the process, and then you get the sun, get photosynthesis again, producing sugar, glucose, and releasing to us oxygen, and this cycle is like a loop, So remember, I said that to my chemistry class, it was the class near the lunchtime. So I told them, if you eat an apple, you never know that you eat a dead human body. And they were very upset. We are going for lunch. Why are you telling us that? Mm-hmm. Well, the apple is coming from what? Maybe a dead dog or dead animal or dead body from the coffin. I mean, disintegrated through times. And all those stuff, dead bodies, corpse, they will be inside the soil, and the bacteria and the fungi will live on them and break them into the original elements. And then the trees will need them to progress in their lives. So we are cycles. So an apple coming from a soil, correct? From the trees. And the trees is fed itself from where? From the soil. And the soil, All those minerals in the soil from where? Dead bodies mostly, correct? And even oil. From where the crude oil is coming from? Those through millions of years, dead bodies compressed by the soil temperature and pressure, and compressed enough to make them very thick oily stuff called crude oil, correct? So even the crude oil is coming from dead bodies. So it's a cycle. It's a cycle itself. So we are going for lunch, but don't be upset with me. But remember, whenever you eat anything, veggies or fruit, you are eating a dead body. Somewhere, hundreds of years, millions of years. I mean, don't be upset, but that's really true. That's really true. I was telling my doctor at Kaiser Permanente, he's a physician, I'm a chemist. He said, don't tell me that, I'm going for my lunch. But that's really true. And they said, you are a scientist, you are a physician. Is this true what I'm telling you? I said, yes. Everything comes from the soil. Anything comes from the soil, it has to go through dead bodies. Even the crude oil, correct? Don't be upset, don't be upset. I apologize up front, I apologize. So I don't want to break your appetite for food. But that's, I tell my wife does not like it at all. She gets very aggressive when I tell her this, you are eating a dead body. But that's really true. That's really true. I mean, that's really true. But they get very upset when you tell them that you are a dead body. But the physician was upset, but then he's a scientist, he knew. He's a scientist, a physician, he knew, he took chemistry. So, from species to ecosystem. Now, the species is a small, tiny group, correct? Small, tiny biological group. They come and live together with the same kind, correct, to make a community. Those type of communities, they come with different type of communities, they can make an ecosystem. So you start with species. Species makes community, correct? This community, they have something in common, correct? They cannot have something not in common. They have to have species, a group of living creatures, humans, whatever you call them. They make species. This species, they make community. This community then, with the same type of behavior, of food, of anything, they share everything. That's a community. But then you have different communities to come together to make what? A system, an ecosystem. And that's what, by definition, correct? So, and this is just to let you type of they're called food web of an African savanna. And you can see the top, those are called the flesh and the meat eaters. Those here, meat eaters here in the top, correct? Some of them are predators, some of them scavengers, such as hyena, correct? Those are flesh eaters, and they're called carnivores. Carnivores are flesh eaters, and the opposite of them is the herbivores, which is eaters of grass. This is grass eater, and this is flesh or meat eaters here. And those are the last one here. Those are producers. Those are trees. Call them producers, correct? Different type of trees. So you can see that's interconnected with all this like a web, correct? It's interconnected. The scavenger will eat the flesh of whatever less weaker animals. The weaker animals will eat insects, and the insects will feed themselves to bacteria, whatever, and then the trees will offer some for those insects, and some of the consumers that feed, and all levels, scavengers, detritivores, and decomposer. So, and you can see, you don't have to worry about this, but at least you know everything at the end is interconnected to each other. The scavenger or the flesh eater, they will eat. Non-flesh eaters, they feed on them, and the non-flesh eaters, they will eat on some other animal or insect. Those insects will come and feed themselves on trees. So that the end is the main producer is our tree. The main producer is really for the whole net here, for the whole web, is the trees. Although it's at the bottom, but that's really providing the whole thing interconnected. So, and we have 4 minutes, and we can. That's the definition. I want you to just maybe print out this one here for the next quiz. If you are asked about definitions, you have them ready, but in the final exam, you have to have them ready, because then it will be no open book, it will be closed book. So make sure that you have this print out, especially with the definition, trophic level, that's the feeding level, feeding status in the ecosystem. Primary producer, those are our trees, hydrotrophs, those are our consumers, correct? Such as rabbits, those animals. And herbivores, they are eater, plant eater, such as our example here, rabbits, deers, and so on. And there's carnivores, those are flesh for meat eaters. And there are some in between them called omnivores. Omnivores, they can feed themselves on plant and animal matters, correct? Not on flesh, but animal matters. So, okay, guys. Parasites, scavengers, decomposers are recyclers. That's really true. So I give you an example on an apple is made of a dead body. Dead body is decomposed to its animal, to these elements, this element back to the environment, and you get scavengers. Again, I want you to make an 2 minutes. Give me 2 minutes just to finish this. I want you to look into this definitions. Scavengers such as hyena, correct? Vultures, those are scavenging. Those are really scavengers like vultures and hyena. They don't really eat fresh food. They mostly eat corpse, because they cannot compete with lions or tigers or cheetahs. They are afraid from them. They just eat mostly the scavenge. Whatever is available most of the time is dead bodies of other eaten animals by bigger animals such as lions, cheetahs, tigers. Detritivores, those are small tiny animals such as ants, beetles. They consume litter, debris, and all the junky stuff. Okay, and decomposers, organism, bacteria and fungi are used to decompose any dead body. I'll stop here. Next time we'll finish, once they finish chapter 2, and the quiz number 2 is posted, and it's open book, correct? You said open book? Yes, it's open book, but no cell phone, please, no cell phone. You are allowed to use anything, but no cell phone, so you can depend on your own. Okay, guys? And if you have any question, just let me know, please. Let me know through the iCollege email. Thank you very much.